All right, everyone, welcome back. Ready for another deep dive?
Always.
Awesome. Well, today we're going to be tackling something pretty amazing, actually. It could redefine, I think, nuclear energy as we know it.
Ooh.
Yeah. And this is direct conversion technology, or DCT.
Yeah.
And, you've shared some really incredible in-depth papers from Dr. Levne Moten.
Yeah, a leading expert in the field.
Leading expert, absolutely. And let me tell you, this stuff, it's wild. I mean, we're talking reactors with no moving parts.
Amazing.
Efficiency that just blows traditional plants out of the water.
Right.
It sounds almost too good to be true.
This is definitely a fascinating area, yeah, with huge potential.
Huge potential. Okay. So for anyone just joining us out there, the typical nuclear power plant, it's all about using heat to make steam, right? Which then spins these giant turbines to create electricity. But DCT seems to be cutting out the middleman here.
You got it.
So what's the big idea?
Direct conversion technology aims to skip that whole steam and turbine step and convert the heat from that reactor core directly into electricity, like a shortcut to clean energy.
I love shortcuts, especially when we're talking about something as crucial as energy, right?
Absolutely.
But how does this direct conversion magic actually work?
Well, there are two main approaches that are being explored, both of them outlined in Dr. Moten's papers.
Okay.
And we've got heat to light to electricity conversion, or HLEC.
Okay.
And then Thermophotovoltaic technology, or TPV.
Got it. HLEC and TPV. Okay, those names, those sound like, I don't know, something out of like a sci-fi movie or something.
It might sound futuristic, but the science behind it is really real.
Okay, all right.
Both techniques actually involve capturing the intense heat that's generated by the reactor core.
Yeah.
And transforming it into, a usable form of energy.
Okay, so less steampunk and more high-tech energy conversion.
Definitely.
But what's the advantage of going direct? Why not just stick with the tried and true steam turbines?
Well, think about all that machinery that's involved in a traditional power plant.
Yeah.
You've got massive turbines, generators, cooling systems, all with moving parts.
Oh, yeah.
That require constant maintenance and are prone to wear and tear.
Right. Makes sense.
DCT aims to streamline that whole process and eliminate a lot of these components.
So fewer moving parts, less maintenance. That makes sense.
Yeah.
But is there more to it than just simplicity?
Absolutely. By going direct, we can potentially achieve much higher energy conversion efficiencies. That means getting more electricity out of every bit of heat generated by the reactor.
That's huge. More bang for your nuclear buck.
Exactly. Plus, DCT systems are inherently more compact and scalable, making them ideal for smaller modular reactors.
Okay, I'm starting to see why you're so excited about this. So we could be talking about smaller, more efficient, and potentially safer nuclear reactors.
Yes.
That's pretty revolutionary.
It really could be a game changer.
All right, let's break down these two approaches a little bit. Dr. Moten's paper, he focuses on HLEC and TPV separately. Let's start with HLEC. This seems like it could just rewrite the rules of nuclear energy.
Yeah, HLEC is all about converting the heat from the reactor core into light, which is then captured by photovoltaic cells to generate electricity.
Okay.
It's kind of similar to how a solar panel works, just with a much different light source.
Wait, so it's like creating an artificial sun inside the reactor?
Yeah.
And then just harnessing its power.
That's a good analogy. We're not talking about actual sunlight here.
Right.
The light that's emitted by the reactor core, it's mostly in the near-infrared range, which is invisible to the human eye.
Okay, so it's more like an invisible sun. But how do you ensure that invisible light is the right kind of light for the photovoltaic cells to use?
Right.
I mean, in the paper, Dr. Moten mentions selective emitters, and they sound pretty crucial.
You're right. They are key to making HLEC work.
Okay.
These materials are actually designed to emit specific wavelengths of light that are perfectly matched to the photovoltaic cell's optimal absorption range.
So it's not just any light. It's like, what, a tailored light beam designed to hit those photovoltaic cells with the perfect energy?
Yeah, you're fine-tuning the light to get that maximum efficiency.
Clever. But how do you even control light at that level? What kind of sorcery are we talking about here?
Not magic, though it might seem that way.
Yeah.
We're talking about cutting-edge material science and engineering. Scientists are using things like photonic crystals and metamaterials to manipulate light with incredible precision.
Okay.
It's like building these tiny, intricate structures that act as, like, traffic controllers for photons, guiding them exactly where they need to go.
Photonic crystals, metamaterials. Okay, it definitely sounds futuristic.
It does.
It reminds me of those sci-fi movies where they have lasers doing all sorts of crazy things.
Yeah.
But I'm still trying to wrap my head around how this actually translates to making electricity.
Think of it like this. The heat from the reactor excites the atoms in these, special emitter materials, causing them to release photons, which are particles of light. By carefully engineering the structure of these emitters, we can control the exact wavelengths of light that they emit.
Okay.
Those precisely tuned photons then hit those photovoltaic cells, which are designed to absorb that specific energy and convert it directly into electricity.
So you're basically orchestrating a symphony of light inside the reactor.
Yeah.
All perfectly timed and tuned for maximum energy conversion.
That's a great way to put it. Harnessing the fundamental laws of physics, like Planck's law and the Stefan-Boltzmann law, and using them to our advantage.
That is mind-blowing to think that we can manipulate light at such a tiny scale to just kind of do our bidding,
Yeah.
It seems like the choice of materials for these emitters and photovoltaic cells would be just absolutely critical.
You're absolutely right. Material science is at the heart of HLEC technology. For instance, Dr. Namoten highlights the importance of materials like gallium antimonide, or GASP, for the photovoltaic cells.
GASP, okay. I'm guessing it's not just any old material that can handle the heat and radiation inside a nuclear reactor. So why gas in particular?
It all comes down to efficiency. GAS-BEV is incredibly good at absorbing the specific wavelengths of near-infrared light that are produced by reactors operating at around 800 degrees Celsius.
Oh, wow.
That's the sweet spot for this type of conversion.
So it's like finding the perfect dance partner, one that moves in sync with the rhythm of the reactor's light.
Precisely. Matching the material's properties to the specific conditions and energy flows within the system.
Okay, I think I'm starting to get the hang of HLEC here.
Yeah.
It's all about this precision engineering and harnessing light at this microscopic level. It's incredible. But what about TPV? How does that approach differ?
TPV also relies on the principle of converting thermal radiation from the reactor core into electricity, but takes a slightly different path.
Okay.
Instead of going from heat to light to electricity, it uses specialized photovoltaic cells that can actually handle much higher temperatures directly.
Direct heat to electricity conversion. No light show involved.
Well, there's still light involved, but it's not the primary focus. Think of it this way. HLEC is like using a spotlight to illuminate the photovoltaic cells.
Yeah.
TPV is more like using a heat lamp to directly warm them up.
Okay.
Both approaches achieve the same goal, generating electricity, but through slightly different mechanisms.
Interesting. So TPV is more about dealing with that intense heat directly.
Right.
What kind of temperatures are we talking about here?
TPV systems typically operate in the range of 800 to 1200 degrees Celsius. That's significantly hotter than the temperatures used in HLEC systems.
Wow, that is hot. I can't even imagine what kind of materials can withstand that kind of heat.
You're right. Material selection is even more crucial in TPV systems. We're talking about materials like tungsten,
Okay.
known for its extremely high melting point.
Yeah.
And various rare earth oxides that have specific properties suited for this type of energy conversion.
Tungsten, rare earth oxides, those sound tough. But if they're working with that intense heat directly, how do they actually generate electricity?
That's where the thermophotovoltaic part comes in.
Okay.
These specialized photovoltaic cells are designed to absorb a wider spectrum of thermal radiation, including infrared light, and convert it into electricity. It's like they have a broader appetite for that heat energy compared to the more selective photovoltaic cells used in HLEC systems.
So instead of relying on those precisely tuned photons in HLEC, TPV is more about capturing a wider range of that heat energy and converting it directly.
Exactly. Casting a wider net to catch more of the available energy.
I like that. That's a good analogy. But in Dr. Namoten's paper, he specifically mentions multi-junction cells for TPV. What's so special about those?
Multi-junction cells are kind of a fascinating innovation in photovoltaic technology. Imagine stacking different types of photovoltaic materials on top of each other, each layer designed to capture a specific portion of the light spectrum.
So it's like having a team of specialized photovoltaic cells, each grabbing a different slice of the energy pie.
That's a great way to think about it.
Yeah.
This multi-layered approach allows TPV systems to be remarkably efficient at converting that wide range of heat energy into electricity. It's like squeezing every last bit of juice out of the fruit.
It's amazing how much complexity goes into just capturing and converting energy at such a fundamental level.
Yeah.
It really highlights the ingenuity of these technologies.
It's truly remarkable.
Yeah. And the potential benefits in terms of efficiency, scalability, reduced environmental impact, that's what makes DCT so exciting.
It's a huge area of research, yeah.
Well, I can definitely see why you're so passionate about it after hearing all this.
Yeah.
It sounds like DCT could address some of the biggest concerns that people have about nuclear power.
Right.
The safety, the efficiency, the waste. But I imagine there must be some pretty big challenges to overcome before we see DCT powering our homes and cities, right?
You're absolutely right.
Mm.
While the potential of DCT is enormous, there are still some significant hurdles to clear.
Oh.
Okay, and as Dr. Neymoten points out in his papers, understanding those challenges is key to unlocking the full potential of this technology.
Well, let's dive into those challenges. What are some of the biggest obstacles facing DCT? And what are researchers doing to try to overcome them?
That's a great question, and that's where things get really interesting.
All right, so we're back and ready to tackle these challenges that are facing direct conversion technology, or DCT. We've talked about its potential to just revolutionize nuclear energy, but as with any groundbreaking technology, I'm sure there are going to be hurdles along the way.
Exactly. DCT might sound like a futuristic dream, but turning that dream into reality, that requires tackling some very real, scientific and engineering challenges.
Well, let's not shy away from the tough stuff. What are some of the biggest roadblocks that are standing in the way of DCT becoming a mainstream energy source?
Well, one of the most significant challenges is finding the right materials, We're talking about operating in these really extreme environments. Intense heat, radiation, you name it. Not just any material can withstand those conditions for very long.
So it's like, what, trying to build a house in the middle of a volcano? You need some pretty hardcore building blocks.
Yeah, that's a great analogy. We need materials that can handle that heat without, melting or degrading or just losing their ability to function properly.
Yeah.
And it's a tall order, and researchers are constantly looking for new materials and ways to enhance their durability.
What kind of materials are we talking about here? I mean, are we talking about some exotic element from the periodic table I've never even heard of?
Well, some of them might sound familiar, but the way that we're using them is really pushing the boundaries of material science. For instance, tungsten, which is often used in, light bulb filaments, that plays a crucial role in DCT because of its, extremely high melting point.
Yeah.
But even tungsten has its limits. So researchers are looking at ways to reinforce it, maybe even combine it with other materials to just enhance its resilience.
So it's about finding that perfect blend of strength, heat resistance, whatever other properties are needed to make DCT work. It's not just about the materials themselves, right? It's about how they interact with each other and how they're assembled.
You're right. It's a multifaceted challenge. For example, even if you have this super tough material, it can still crack or degrade over time because of thermal stress, the constant expansion and contraction that's caused by all that intense heat. So designing systems that can actually accommodate those stresses and prevent any catastrophic failures, well, that's another huge challenge.
It sounds like a delicate balancing act, finding materials that can withstand the harsh environment while also being compatible with each other and the overall system design. I imagine radiation is another major factor that adds to the complexity of it all. How do you protect these materials from being bombarded by subatomic particles?
That's another critical challenge. And it's where things get really interesting at the atomic level. Radiation can actually damage the structure of materials, weakening them over time or even altering their properties in unexpected ways. You can think of it like a constant barrage of tiny bullets just hitting the walls of your reactor.
Ouch. So how do you shield those walls from that atomic onslaught?
There are actually several approaches that are being explored. One is to actually develop these radiation-resistant coatings that act like a protective layer, absorbing or deflecting those incoming particles. It's like giving your materials a suit of armor.
Okay, that makes sense. Coatings can only do so much, right? Are there other ways to kind of protect those materials from the inside out?
Absolutely. The other approach is to actually use materials that are inherently more resistant to that radiation damage. And this involves delving into the world of nuclear physics and material science, understanding how different elements and their isotopes interact with radiation. It's like breeding a new species of plant that can thrive in a radioactive wasteland.
Wow, it's incredible to think that we're manipulating materials at such a fundamental level to make this technology work. But even with the most resilient materials, I imagine heat management is another huge challenge. Keeping those systems from overheating, that's got to be crucial, right?
Absolutely. You're right. Even with the best materials, excessive heat can still reduce the efficiency of the system or even lead to component failures. It's like pushing a car engine too hard. Eventually, it's going to overheat and just break down.
So it's all about finding that Goldilocks zone. Not too hot, not too cold, right? where the system operates at peak performance and longevity, how do you even begin to manage those extreme temperatures?
It's a really complex engineering challenge, and there are several strategies that are being employed. One is to develop these advanced cooling systems that can efficiently dissipate heat away from those critical components. Imagine these, tiny intricate networks of channels and pumps circulating specialized coolants to keep that system from getting too hot.
It's like having a miniature air conditioning system inside the reactor core.
That's a good analogy. And beyond those active cooling systems, researchers are also exploring passive cooling techniques using materials that can absorb and release heat as needed. It's like having these built-in thermal sponges that help regulate the temperature.
That's pretty neat. So you've got these carefully engineered materials working in tandem with these intricate cooling systems to keep everything running smoothly. But I remember you mentioned something called spectral mismatch earlier. What exactly is that, and why is that a challenge?
Spectral mismatch is all about making sure that the light that is emitted by that heat source, whether it's the reactor core in HLEC or those specialized emitters in TPV, it's perfectly aligned with the absorption range of those photovoltaic cells.
Okay.
You see, if there's a mismatch, it means some of that precious light energy is just wasted. Like trying to, power your phone with a flashlight that emits the wrong color of light.
So it's like trying to tune a radio to the right frequency. You need that perfect alignment to get a clear signal, or in this case, maximum energy conversion.
Exactly. And that's where those, futuristic sounding photonic crystals and metamaterials come into play again.
Right.
These really carefully designed structures, they act like tiny prisms and filters, shaping and guiding the light to ensure that it hits those photovoltaic cells with the right energy at the right angle. It's like giving each photon a personalized roadmap to its destination.
It's amazing how much precision goes into this process. It's not just about like brute force energy conversion. It's about finesse and control at a microscopic level.
Absolutely. And mastering that control, well, it's key to maximizing efficiency and making DCT a truly viable alternative to those traditional energy sources.
Okay, so we've covered the material challenges, heat management, and spectral mismatch. All of these seem like pretty significant hurdles, but I have a feeling there's one more big challenge lurking in the shadows here. Cost.
You're right. Cost is always a factor, especially when you're talking about developing a completely new energy technology. And DCT is no exception. Some of the materials that are involved, like those rare earth oxides and specialized photovoltaic materials, they aren't exactly cheap to produce.
I can imagine. It's like trying to build a spaceship out of diamond-encrusted titanium. It's going to cost a fortune.
That's one way to put it. But you're right. The upfront cost can be significant. However, it's important to remember that this is an emerging technology. And as the research progresses and production scales up, those costs are likely to come down. Think about the early days of solar panels or even computers. They were initially incredibly expensive. But over time, as the technology advanced and production became more efficient, well, the prices dropped dramatically.
So it's about playing the long game, right? Investing in research and development now with the hope that those initial costs will eventually pay off in the form of cheaper, cleaner, and more accessible energy in the future.
Precisely. And that's actually where Dr. Namoten's proposal for collaboration comes in. By bringing together the best minds and resources from around the world, well, we can accelerate the pace of innovation and problem solving.
Yeah, collaboration is key to tackling these complex challenges, especially in the scientific and engineering world. But before we dive into the details of Dr. Namoten's proposal, let's take a step back and consider the bigger picture. Even if we manage to overcome all of these technical and economic hurdles, are there any potential downsides to DCT that we should be aware of? Are there any risks or unintended consequences that we need to consider?
That's a crucial question, and it's one that researchers and policymakers are taking very seriously. While DCT offers these tremendous potential benefits, it's important to approach this technology with a balanced perspective, acknowledging both the opportunities and the challenges.
All right, so we're back and ready to kind of explore the potential downsides and implications of direct conversion technology.
Yeah.
I mean, it's easy to get caught up in the excitement of a groundbreaking technology like this.
Right.
But, as we all know, it's important to look at both sides of the coin.
You're absolutely right. Every technological advancement comes with its own set of, challenges and potential risks, and DCT is no exception.
Right.
It's not about being, overly optimistic or pessimistic, but rather having this clear-eyed view of the complexities involved.
Well, let's jump right in. What are some of the potential downsides or unintended consequences that we need to consider when it comes to DCT?
One concern that often comes up with, any nuclear technology is the risk of proliferation. The materials and knowledge involved in, building and operating nuclear reactors, well, that could potentially be misused for nefarious purposes.
Right, and that's a serious concern, and one that I'm sure is at the forefront of everyone's minds when we're discussing nuclear energy. How do we ensure that DCT doesn't contribute to the spread of nuclear weapons?
It's a multifaceted challenge, and it requires a global effort. International cooperation, strong regulatory frameworks, strict safeguards, they're all essential to prevent the misuse of this technology. Think of it like building a high-security vault around the technology with multiple layers of protection to prevent any unauthorized access or diversion.
Okay, it sounds like a lot of responsibility, but it's reassuring to know that these concerns are being taken seriously. What are some other potential downsides or challenges that we should be aware of?
Another important consideration is the potential for economic disruption. A widespread shift to DCT could significantly impact existing industries, particularly those related to fossil fuels.
That makes sense. If DCT becomes a major player in the energy sector, it could displace jobs and create a ripple effect throughout the economy. How do we manage that transition in a way that benefits everyone, not just the companies and workers involved in the new technology?
It's a crucial question, and one that requires careful planning and foresight. Investing in retraining programs for workers in those transitioning industries.
Yeah.
Fostering the development of new skills, supporting communities that may be impacted by these economic shifts.
Right.
These are all essential steps.
It's about ensuring a just and equitable transition, one that doesn't leave anyone behind.
Exactly.
But even if we manage to navigate those economic challenges, are there any inherent limitations to DCT that we should be aware of?
Well, one thing to keep in mind is that DCT, like any energy technology, it's not a magic bullet solution to our energy challenges. It's not going to, single-handedly solve climate change or eliminate our dependence on fossil fuels overnight.
So it's important to manage expectations, right?
Yeah.
DCT is a promising technology, but it's not a quick fix.
Exactly. It's going to require, continued research, development, investment to bring DCT to its full potential. Yeah. And even then, it will likely be part of a larger portfolio of solutions alongside other renewable energy sources, energy efficiency measures, smart grid technologies.
It's about having that diverse toolbox and using the right tools for the job, right?
Exactly.
But speaking of tools, let's talk about the international collaboration that Dr. Nemotin is proposing. Why is that collaboration so crucial for the advancement of DCT?
Well, DCT is a complex and multidisciplinary field. It requires expertise in areas like nuclear physics, material science, engineering, even economics and policy. By bringing together, the best minds from around the world, we can pool our knowledge, our resources, our perspectives, and really accelerate the pace of innovation.
It's like assembling an all-star team of scientists and engineers, each with their own unique skills and insights to tackle this grand challenge.
That's a great analogy. And beyond just, the scientific progress, international collaboration also, it fosters diplomacy, promotes cultural exchange, and builds trust between nations.
So it's a win-win situation, both scientifically and diplomatically. But, let's be realistic for a moment here. Even with all the best intentions and a dream team of experts, what are some of the biggest obstacles that this collaboration might face?
Well, one challenge is simply the sheer complexity of coordinating those research and development efforts across different countries, different institutions, different research cultures, funding mechanisms, and regulatory environments. All of that can create logistical hurdles that need to be overcome.
It's like trying to conduct an orchestra with musicians from all over the world, each playing a different instrument, each speaking a different language, right? It takes a skilled conductor to bring all those sounds together harmoniously.
That's a great way to put it. It requires strong leadership, clear communication, and a shared vision to make this kind of international collaboration truly successful.
Well, it sounds like a challenging but incredibly worthwhile endeavor.
It is.
But even if this collaboration achieves its goals and DCT becomes a viable energy source, what does that mean for the future of energy as a whole? How will it reshape the way we power our world?
That's the big question, isn't it? If DCT lives up to its potential, it could fundamentally alter the energy landscape.
Right.
We could see a shift away from that centralized power generation towards a more decentralized and resilient grid, powered by these smaller modular reactors that can be deployed closer to where the energy is needed.
So it's about moving away from those massive centralized power plants and towards a more distributed energy system, similar to what we're seeing with solar and wind power.
Exactly. And this kind of decentralized energy system, it offers numerous advantages, increased reliability, reduced transmission losses, greater energy independence for communities and regions.
It's a vision of a future where energy is more accessible, more sustainable, and more equitable. But ultimately, the success of DCT and its impact on the future of energy is going to depend on a multitude of factors: scientific advancements, economic realities, public perception, political will.
You're absolutely right. It's a complex interplay of forces, and predicting the future is always a risky business. But what we can do is stay informed, engage in thoughtful discussions, and support the research and development that'll help us navigate this exciting and uncertain future.
Well said. It's been an incredible journey exploring the world of DCT with you.
It has.
It's a technology that sparks both imagination and debate.
Yeah.
And it's one that we'll undoubtedly be hearing more about in the years to come.
So as we wrap up this deep dive, what's one key takeaway that you'd like our listeners to walk away with? I'd say this: DCT represents a bold and innovative approach to nuclear energy, one that holds tremendous promise for a cleaner, more sustainable future. But like any powerful tool, it needs to be handled with care, responsibility, and a clear understanding of both its potential benefits and risks. The choices that we make today, they will shape that energy landscape of tomorrow. And it's up to all of us to engage in this important conversation and help guide the development of this transformative technology.
That's a powerful message, and one that I think will resonate with our listeners out there. Thanks for joining us on this deep dive into the world of direct conversion technology. Until next time, keep exploring, keep questioning, and keep diving deep into this fascinating world of science and technology.